love your curves.
All right, this is Mr. McMurray on Station KMUR, KMUR. All right. Anyhow, all the hits all the time. There we go. Now we're going, speaking of hits, we're going into physics. All right, involving physical things. Let me see. For some reason, it's not giving me the option to do a pin. But anyhow, all right. So first off, we talked a little bit about fluid resistance moving through air or water or any other kind of fluid. And because of that, we said that the fluid resistance depends on how fast you're moving through the fluid or how fast the fluid is moving over you, if it's like wind blowing over you. The object's frontal surface, how much it catches the wind or the fluid, and finally the density of the fluid. The denser the fluid, the harder it is to move through it. Okay, now we're going to talk about a principle called terminal velocity, but before we do that, we need to go over some things, and so let's switch media here for a second. I'll be right back. All right, here we go. We're back again. Now, let's say I have a bowling ball, and I'm going to drop it off the roof, okay? First, I would check and make sure there's nobody, or at least nobody I don't want to hit with it, down below, and then I would drop it. Now, when I first have it, the only force acting on it, when it's on my hand, there's the force of gravity, and then there would be the normal force of my hand holding it back up, and that would give it a net force of 0. So it would just sit there on my hand. But as soon as I let go of it, okay, the only force acting on it is gravity at first. Okay, gravity starts to push it down. But as it starts to move, what do we find out about air resistance? It picks up, okay? And so as it starts to move, we start getting air resistance pushing back against it, okay? And so it accelerates less, okay? Then as it goes farther and farther, it speeds up. So as an object speeds up, what does that do to the amount of air resistance? It speeds it up. So it's reducing the speed at which it accelerates. And then finally, it's going to reach a point where it's going so fast that the air resistance is equal to the force of gravity pushing down on it, and so we have a net force of 0. So what happens? Does the ball just stop and levitate in midair? No. Okay, net force of 0 doesn't mean it's not moving anymore. The net force of 0, remember, means it is not changing, okay? And so once it hits this point, it will not speed up anymore. Now the air resistance is equal to the force of gravity, and so there is no acceleration, and it will not go any faster than that speed, okay? And that speed is called the terminal velocity because it's the final or the end velocity. It can't go any faster than that. Does not mean it's going to die from speed, okay? That's a whole different thing. All right, but anyhow, now back to the other notes. All right, so now we're back to terminal velocity. The velocity that is reached when the force of the air resistance equals the force of the gravity so that the falling object no longer accelerates. It's still moving, but it's going to reach a top speed, and it cannot go any farther than that. And so, for example, if you drop a penny off the Empire State Building, okay, at some point as it will start to speed up, but after it reaches a certain speed, then it will cancel out with the air resistance against it, and so it will not go any faster. And that is why you cannot drop a penny off the Empire State Building and kill someone. It will hurt, but if it hit an eye or something, it might do damage. But for the most part, you're pretty safe if you're having to be in New York watching under the Empire State Building. All right. Now, another example that would be parachutes. When you jump out of a plane, first of all, you don't just jump standing straight up and down because then you wouldn't have much air resistance and you would go too fast, okay? You usually spread eagle yourself out, spread out, and so you have the most air resistance possible so you don't go down real fast. And you would eventually, as you go down, you would speed up, and eventually air resistance would speed up, and you would reach a terminal velocity. Now, depending on your weight and everything, it might be somewhere around 50, 60, 70 miles an hour, maybe up to 100 and something, okay? But at that point, you would reach a terminal velocity. Now, the bad news is, if that's your terminal velocity and you hit the ground, you're probably going to die. Occasionally, you'll hear about someone who hit some tree branches or landed in the water or something that broke his fall, and he did not die. The reason that's on the news is because that's not what usually happens. Usually you die, okay? And so I don't recommend that. But to stop that, what we do is we pop a parachute, poof, pops up, and now you've increased your surface frontal area, all right, which we remember from up here, total frontal surface area. Now we have a great more frontal surface area, boom, a lot more air resistance, and so we reach a terminal velocity much quicker, okay, and hopefully about 5 to 10 miles an hour. So when you come down, you will lightly touch down and just kind of boom, hit the ground and walk away from it. Very nice. All right. And so they example of using terminal velocity or something to slow down the terminal velocity would be our parachutes. Okay, so parachutes would be an example of doing something like that. All right. Now, we're going to talk a little bit about gravity because we've really kind of already talked about gravity a little bit there. What is gravity? Everybody kind of knows what gravity is. We've all felt gravity at some point in our lives. But what is gravity? What causes it? All right, the law of gravitation, or universal gravitation, was discovered or explained at least by Sir Isaac Newton. Not like before he discovered it, things didn't fall, they still fell, and gravity happened. It's just that we didn't know how it happened. So the law of gravitation is this. Universal gravitation says any two masses, any two objects exert an attractive force on each other, okay? So that means between you and the desk, there's an attractive force. Between you and your pencil, there's an attractive force. Now, it's not very much, so you don't feel it, which would probably be a good thing. Otherwise, you go walking down the street, you'd be attracted to everything on both sides. That's not a good thing. All right, so what does the attraction depend on? Well, it depends on the mass of the objects. The greater the mass of the objects, the greater the pull of gravity, and vice versa. In fact, the only gravity we feel, really, for all practical purposes, is the Earth. Okay, and that's because it is extremely large, billions of times bigger than we are. Actually, hundreds of billions probably, but we won't get picky on the numbers. But basically, that's the only thing we feel the pull of gravity from, because it is the only thing big enough or has enough mass. Okay. And so we would say that the mass are directly proportional to the force of gravity. If you increase the masses, then you will increase the force of gravity that you feel. All right. Now, the other thing is the distance between the objects. Okay. And so basically, if the objects are close together, then you are going to feel a lot more force of gravity. If they're farther apart, you're going to feel less force of gravity. So the greater the distance between the objects, the pull of gravity is not just less, but it's exponentially less. In other words, it gets a lot less. As you get farther away, it really starts to decrease. All right. Now, so we say that the distance is exponentially and inversely proportional. In other words, inverse, if you get the distance gets bigger, the force of gravity gets smaller. And not just a little bit, but exponentially smaller. Okay. All right. And so basically, the distance between us and the Earth is actually the distance between us and the center of the Earth. Okay, so it's really the center of the two objects, center of gravity. Okay, and on Earth, that's pretty much the same. Even if we went to the tallest mountain, Mount Everest, which is about 5.5 miles above the sea level, you might lose a third of a pound or half a pound. Very, very minimal amounts, okay? So pretty much the force of gravity, as long as you're on the surface of the Earth, is pretty much the same everywhere. Even if you're in an airplane, which also probably gets 5, 6, 7, maybe 10 at the most, but probably less than that, 5 to 7 miles above the surface, just like Mount Everest, you might lose a third of a pound, but you're not even going to notice that. You're not going to be walking down the airplane aisle saying, wow, I feel so light now. Okay, it's not that big a deal. All right, so on Earth, anywhere on Earth, the distance and the mass is pretty well constant. So the acceleration due to gravity, in other words, how fast does gravity pull things, or G, we talked about on our worksheet the other day, is 9.8 meters per second squared. In other words, every second you would increase your speed 9.8 meters per second. Okay, so after 1 second, you're going about 10 meters per second. After 2, you're going 20, and then 30 and 40. And if you put that in miles per hour, that'd be like 20 miles per hour after 1 second, and that would be 40 miles per hour after 2 seconds, and so forth. You see how that would work. So you don't have to fall very long before you would be going pretty fast. Now that also, of course, does not apply, do not include air resistance, which would slow you down a little bit. But still, you don't want to fall off a very tall object. Okay, falling off the roof of a one-story house might not be too bad, might break a leg or something, but probably nothing too bad unless you land on your head, because it only takes about a second or so to fall that far. Okay, all right. Now, technically, since the elevation is different in different places, your force of gravity, your distance does change a little bit, okay? So technically in paradise, and this is probably actually for Dallas, but look this up on a web page. You can look up anywhere on Earth, and it will tell you what the actual G value is for where you're at. And technically it's 9.79472 meters per second squared, but we'll just go with 9.8. How about it? Why don't we? All right. All right. Now, In line with gravity, we need to talk about mass and weight, okay? Weight is really just a measure of the force of gravity on an object, okay? Your weight is how much gravity is pulling down on you toward the center of the earth, okay? And so that is your law of gravitation. I mean, that is your weight, okay? Now, we would normally measure your weight in pounds. In the metric system, we would measure it in newtons because it's a force of gravity, so all forces are measured in newtons, okay? Mine would be about 945 newtons, give or take a little bit, depending on if I've gained weight or lost weight. And so the way we calculate your weight is just like force. If you remember from Newton's second law, force is equal to mass times acceleration. Well, your weight, which is the force of gravity, is equal to your mass, which would be in kilograms. If you took your pounds and divided it by 2.2, that would give you the kilograms. So roughly about half your weight will tell you I weigh 200 pounds, but it's about 94 kilograms. Okay, that's my mass. Times g, which is 9.8, the acceleration, 9.8 meters per second squared. And I would come out with my weight in newtons is about 940 newtons. Okay, so next time someone asks you how much you weigh, say, hey, I weigh 940. I say, what? But you just have to tell them it's newtons. It'd be more fun if it was a small number, but sorry about that. All right, so newtons is equal to the number of kilograms you weigh times 9.8 meters per second squared, at least as long as you're on Earth. Now, your weight in newtons, then would be the same general formula, is your weight in pounds times 4.45. Okay, so if you want to do that, that will also give it to you. So if I took my 200 pounds, multiplied it by 4.45, and I would end up with about 940 newtons or so. So you can take your weight in pounds and multiply it by 4.45 because there's about 4.45 pounds in a newton. Okay? All right. Or, no, I did that wrong. There are 4.45 newtons in a pound. Sorry, there we go. So newtons are quite a bit smaller than pounds. All right. All right. This is an apple made out of foam rubber, kind of squishy thing, and it's about 1 newton. So it's a Newton's apple is what it's called, but it's exactly 1 newton. So it's not very heavy. So it takes about 4.5 of those to even make 1 pound. So it's a little smaller. Now, mass, on the other hand, is different. It is, I can get my computer, here we go. The amount of matter that something is made of, okay? Now, the amount of matter has to do with how much atoms or mass is in it. Okay, and it cannot change. How much you are is how much you are. If you go up to the moon, there's still just as much of you as there was on Earth. However, your weight will be different because it depends on gravity. We measure weight with a scale. So we put a scale and then we hang something on it. Gravity pulls down on it, or we get scales and I step on them, and gravity pushes me down against the scale, and the scale pushes back up with the normal force, and we measure that is your weight. Now, if you go someplace where there's less gravity, such as the moon, where there's only 1/6 as much, then I won't weigh as much. Okay, I may only weigh, let's see, 1/6 of 200 is about 33 pounds. Okay, so I would weigh only 33 pounds on the moon, but there's still just as much of me as there ever was. And so that would be my mass, and my mass is measured with a balance. And if you put a balance and you balance something on Earth, and then you go up to the moon and balance it, it will still balance, okay? And so the amount of mass that something has does not change. It's constant, whereas weight depends upon gravity. All right, we're going to stop right there, and we will be back for some more notes on free fall and Newton's third law and finish up.